All right, let's get started. Is there any questions, any questions, any questions? Okay. All right, so today we're going to do something real fun. We're going to prove that square root of 2 is irrational. All right, but before we do, there is a few other things that we want to take care of. Now we can get right to it. So just to recall, a rational number, a number is rational if we can write it as a fraction made of integers. You know, I did say fraction and I did write quotient, managed to spell it right. Fraction is fine, but the set theory symbol of the rational numbers is Q for quotient. So it makes it easier to remember. It's the quotient set of the integers. All right. So last time I mentioned that it's much easier to prove that a number is rational than to prove it that it's irrational, because it's hard to prove a universal negative, right? No matter how hard we try, we cannot write this this number as a fraction of two integers. How do you get about proving that? That sounds like a really difficult undertaking, because you can try examples, but guess what? Anything you and I can do is finite. And there are infinitely many numbers, so that is not feasible. So this is the tricky part, when somehow you have to talk about every effort or every possibility all at the same time. So we're going to say square root of 2 is not rational. A number that's not rational, we call it irrational. There are famous examples for irrational numbers. Actually, I want to show you a third one. Now, square root of 2 is the one we come up with, but any number that if it's not a perfect square, you put it under the square root, that's going to be irrational. So square root of 12 is irrational. Not just square root of 13, but also square root of 12. So square root of 2, square root of 3, square root of 5, square root of 6, square root of 10, square root of 12. It has to be an exact perfect square, otherwise it's as bad as irrational. So that's one group. The other group is pi. Pi comes from geometry, has a lot to do with a circle. When we deal with the circle, I want to ask you, don't enter 3.15, don't enter 3.14. Push the pi button. That's a much nicer precision. You can round at the end, but if you round up numbers in the middle of the problem, that's those little sloppinesses. You don't know whether they add up or cancel out each other. So you have to assume the worst. You have a pi button. Now, today we're going to prove that square root of 2 is irrational. Pi irrational, that's much harder. That's calc 2, actually, not even calc 1. Right now, you know, gun to my head, I don't think I can do it. And there is one more number that I would like to show you, and that's called E. I think it was named after a mathematician, Euler, but it's perfect because it has to do with exponentiation. And so okay, it's barely visible, but you see there, e to the x right there, it's in light blue over capital L, capital N, that's e to the x. So you have to push that button, but first the second. And then you see what the calculator starts, e to the. So if you want to look at e, how about e to the first power? And that's e, that's another quite famous irrational number that you might see over your studies. It will be, I think the first time it will be really, really useful is in calculus. So you might not see it. Well, you have seen it now. Okay. All right, so we're going to prove this statement by contradiction or indirect proof. So this is going to be a new type of proof, indirect proof or proof by contradiction. And I actually like both names, proof by contradiction. But before we start the proof, a little bit of the philosophical background. Don't worry, it's not going to be difficult. Suppose we have a statement and another statement, and then we make something that I'm going to refer to LCS. It's going to be short for a logically correct step. Right now, let me show you. I wrote it down. We showed it last time. So what is a logically correct step and what isn't? It's kind of, we are born with that sense. So I'm going to show you two examples. Don't worry about whether it's true or not. Look at whether the conclusion is justified or not. So the first is, every dog is cute is a statement. Sally is a dog is another statement. And the conclusion, therefore, Sally is cute. The second one, every cat is sleepy. Claire is sleepy. Therefore, Claire is a cat. What do you think? Okay, I zoomed out perfectly right. Does one of them seem pretty convincingly true? Does one of them seem pretty suspicious? Right, well, but the conclusion is that, therefore, Claire is a cat. Well, actually, so happens, this is a valid conclusion. Every dog is cute. Well, Sally is one of the dogs, and if every dog is cute, then Sally is forced to be cute. If Sally is a dog, I don't know, here are the dogs. Here are the cute things. I can say subset. And so any dog is automatically cute. I think this one is suspicious because, yeah, every cat is sleepy, but there are plenty of dogs that are sleepy or math teachers at the moment that are sleepy, right? So just because you're sleepy, that doesn't mean you're a cat. Now, if the first sentence said only cats are sleepy, now that would make a difference. You see how this is not really a justified step? Because it doesn't say only cats are sleepy. It just says cats happen to be sleepy, but plenty of other things could be sleepy. So actually, I'm not going for true false. This is a valid conclusion, as we say in physics and as we say in philosophy or in logic, and this is not a valid conclusion. Well, I thought this would go better, but so basically, let's just assume for now that we all are on the same page about logically correct steps. We kind of feel the same way, whether a step is correct logically or not. So here's a really important fact. If statement A is true and we arrive to statement B using a logically correct step, whatever that is, statement A is true, and we arrive to statement B by starting at A and making logically correct step, or more than one, but they're all logically correct. So this is not, the sentence is not finished. So suppose there is a starting statement A, and it's true. And then we're going to start with A and make conclusions from A. And we conclude to another statement using logically correct steps. Then that statement is also true. It has to be. So then statement B is true. So we can sort of say, do a shorthand and say truth only implies truth. So if this statement is true and this statement is true and these steps are all logically correct, then these are all true statements. That's how we prove things, right? We just start with something we establish to be true, and we conclude, we take it from there. Now the question is, what do we think if we start with a false statement and we make a logically correct step? What can we say about the statement that we arrive to? What if we start with a false statement and we make conclusion, right? So when I was a student and I was asked this question, I proudly had the wrong answer. I said, yeah, false. Truth implies truth. False implies false. That sounds about right. But actually, that's not the case. Whenever you start with a false statement, it's a surprise party. It can go either way. So what if it's the statements we arrive to could be false or true? All right, I'll demonstrate, because that was a surprise to me. Here is a false statement. Seems pretty wrong, right? False. Now, here is the logically correct step. If two things are equal to each other, they will remain equal after I do the same thing to them. So these two things, if they started out equal, they will remain equal after I subtracted 6 from both sides. That is a logically correct step. Equal things will remain equal after subtracting 6 from both of them. Still false, right? But now I'm going to say, here is the next step. If two things are equal, they will remain equal after we square them. That's true. So for statements, we have no idea. Sometimes false, sometimes true. It's a little surprise party. But truth only implies truth. So if you know you started with a true statement and your steps are logically correct, you can make 1,000 statements to arrive to the 1,000th, and they all will be true. With a false statement, we never know. So let me ask you this. We start with statement A. Could be false, could be true. We don't know. We make logically correct steps. I'm going to start abbreviating. This is short for logically correct steps, and arrive to B, then C, then D, and we find that D is false. Does that tell us anything? Well, that should tell us something about A. So we start with a statement A, we make logically correct steps and arrive to B and then C and D, and we find that D as a statement is false. What can we then state about A? With certainty. Look, truth only implies truth. So if we ever arrive to a false statement, we must have started with a false statement, because truth will never give birth to a false statement. Only false one can, right? So then statement A must be false. We have a little bit of an asymmetry here, because if the statement D is true, that tells us nothing about A. It still could be true or false. But if we conclude to a false statement, that tells us that the statement we use to step from must be false. Because if it was true, then truth only implies truth. Does that make sense? So say we got A to B to C. By the way, this is the notation for logically follows. I conclude, implies. I'm already using those words. They're kind of interchangeable. So there are two cases. If D is true, we learned absolutely nothing. It could still be anything. If D is true, we learn nothing. But if D is false, we know A cannot be true. Because if A was true and our steps are logically correct, then B is true, and then C is true, and then D is true. If D is false, then we know A is false. Right? So why is it called indirect proof? Sometimes I think I had a teacher who thought about this like scratching your, it's just, you know, cumbersome, difficult. It's strange, but indirect proof is when it's not that we prove our statement to be true, but we prove that its opposite is false. Because it's easier to prove about the statement that it's false. We prove that the opposite of our statement is false. Here, if I say the sky is blue, but then we have to formulate the opposite of our statement, and that takes a little bit of work too. For example, if I say the sky is blue, then the opposite is not the sky is red. Basically, the opposite of the sky is blue is the sky is not blue. It is not true that the sky is blue. That means it could be any other color. So you have to sort of cover all the cases. Between a statement and its opposite, exactly one is true. They cannot both be false or both be true. And they kind of cover everything. So the opposite of the sky is blue is the sky is not blue. So one tricky part about indirect proof that we have to formulate the exact opposite of our statement. Now, what we want to prove is that square root of A is not a rational number. So the opposite is going to be square root of 2 is rational. So we're going to prove this statement false. How? We're going to assume this statement to be true, and we're going to make logically correct steps and arrive to an obviously false statement. And that does it. So does this make sense? So we formulate the opposite of what we want to prove. That's why it's called indirect. What we want to prove and conclude from it something obviously false. And the watchword is obviously. And conclude other statements using logically correct steps until we arrive to an obviously false statement. And that does it, right? If we arrive to an obviously false statement, then the very first statement must be false. And that was the opposite of our statement. So that makes our statement true. It looks odd about, or shall we say indirect, but it's an incredibly powerful proving technique. It's very, very powerful. All right, let's get started. I kind of want to do it differently. You know, there is a video that I'm going to post where I prove this, that square root of 2 is irrational. But today I want to kind of do another sort of a proof because I think it might be easier. So all right. So claim square root of 2 is irrational. Now, all proofs by contradiction will start with the same first 5 words, and that is, suppose for a contradiction that. And now we have to formulate the opposite of our statement. The opposite of square root of 2 is irrational is square root of 2 is not irrational. That means it's rational. So we're going to assume that square root of 2 is rational and arrive to something obviously crazy. That square root of 2 is rational. Okay. Those of you who are paying attention, are you still on board? Is there any questions I can answer right now? This is fun stuff. I don't want to leave you behind. Okay. All righty. Yeah, that's it. So, well, what does it mean rational? That means we start concluding. Conclude. That means that there exist integers a and b not 0, such that a over b is square root of 2. That's what it takes to be rational. If a number is rational, that exists. They could be crazy, they could be strange or large, but there exist 2 integers. So that when we divide, we get square root of 2. And now maybe, I don't know if I should do it. All right. So now we're going to conclude. Square root of 2, there is not much we know about it. We know that if we were to square it, we would get 2. So let's square both sides. Then the right-hand side is square root of is 2. We got rid of the radical. And then how do we square a fraction? Well, a over b squared is a over b times a over b. And that's a squared over b squared. And a and b are integers. Here is another conclusion. If a is an integer, a squared is also an integer. If b is an integer, b squared is also an integer. Now we're going to multiply both sides by b squared. And now we're back to the land of not just rational numbers, but integers. Both sides are now integers, right? And I think we can say that both sides are positive integers. Okay. I'm still hesitating. Okay. So you can watch the video. That's going to have this. So I'll try this new thing. I never tried this because there are several ways to go and find an obviously crazy statement. One of them has to do with the prime factorization. So here is kind of an unrelated but true statement claim. Square numbers have only even exponents in the prime factorization, in their prime factorization. And it's simply because of the rules of exponentiation. If you have a number and I don't know, let's have a 2 power there. Say this is 2 squared, this is 3 to the first power, 5 to the third power. This number has plenty of odd exponents. But what happens if we square it? Well, first of all, that means we can square it piece by piece, right? 2 squared squared times 3 to the first power squared times 5 to the third power squared. I think this is the clearest one. That oh yeah, every exponent will double, right? So what we're left with n squared is, I could say 4 squared, but now I want to say 2 to the fourth power times 3 to the second power times 5 to the sixth power. Because see what I'm trying to say? If a number is a square, then the prime factorizations only have even exponents. Maybe I should have said it a little better, that if a number is a square, let's start with the number first. It has a prime factorization with all kinds of exponents. But when we square, all the exponents double. Does it make sense? And by the way, 0 is an even number. 0 is divisible by 2. There's no remainder. Does it make sense? Okay. And so if we look at a squared equals 2b squared, there is going to be trouble with the prime factorization of the two sides. You remember, prime factorization is unique, and it's actually called the fundamental theorem of arithmetic, so it's important. So a squared and b squared both have an even number of 2 factors. And that includes 0. And then there is one more, right? It is another one. 2b squared then has an odd number of 2 factors. So which one? You know, the two sides are equal. The prime factorization is unique, so something is wrong here, right? B squared, 2b squared has an even number, or odd number of prime factors. Because it's twice a square, right? Every square has an even number of 2 factors, 0 or a positive even number, and then we add 1 when we just throw in this one, because b squared, a square, has even of them. That's one thing. And then, but 2b squared equals a squared. A squared is a square. A squared is a square. Therefore, it has an even number of 2 factors. I keep forgetting to say even number of 2 factors in their prime factorization. 2 factors. All right. And now we can go back to why is it called a proof by contradiction? Because we have 2 statements and we have no idea which is true, which is false, but they cannot be true at the same time, right? The number of 2 factors in 2b squared are at the same time odd and even, right? And so, and that's very, very typical, that instead of arriving to an obviously false statement, rather, we arrive to two conflicting statements that cannot be true at the same time. They can be false at the same time. Well, not in this case. But they cannot be true at the same time. So one of them, at least one of them is false, we're done. We derived an obviously false statement. We don't know which one, but they're both, we arrived to both of them, right? Oh, that's right. So the last two statements conflict with each other, or contradict each other, so both cannot be true. Sometimes they can be both false. You can say, well, this number, when I divide the remainder, when I divide by 7, the remainder is 1. No, when I divide this number by 7, the remainder is 5. 1 or 5, they can be both false, right? This one is a little different, but if they cannot both be true, then one of them is false. We arrive to a false statement. Our starting statement must be false, so we're done. There are all kinds of symbols for contradiction, because this is just too much writing. Sometimes you see like what do you have when you have a storm? I think you understand. And then this is also a pompous happy sign of we're done. So that is how it goes. And if you think about it, what's going on? So take an odd number. If you square an odd number, it will remain odd, right? Because just think prime factorization. If a number is odd and you square it, then it can only become even if suddenly in the prime factorization a 2 appears. Well, where would it come from? It's not in the number or in the number, and you're just doubling what you have. So an odd number squares to an odd number. But if you have an even number, then it's after squaring, it's actually going to be divisible by 4, because you're duplicating everything in the prime factorization when you're squaring things. So if you think about it, I guess this is a similar statement to say that the existence of a square number that's even but not divisible by 4. You can't have one of them. I think that's somehow similar. Same neighborhood. I'm too tired to actually know. If we square a number, if we square an integer, it's either odd, or if it's even, it's actually divisible by 4. You can't go half of it. You can't have a square number that's divisible by 2 but not by 4. That would be an even number of 2 factors causing that. Integer, it's either odd or divisible by 4. I think that's related, yeah. You cannot have a square with just a lonely 2 in the prime factorization. It just cannot happen. Okay, any questions? Proof by contradiction, it's all over the place, by the way. Mathematicians, you would not be able to survive, not in the next class, but in higher level mathematics, the real stuff. When we prove things, I don't think I could go by without contradiction. Every time I said there is no other way to do this, I had to eat my words. So I'm not going to say that there are proofs that only contradiction can take care of them. But boy, I might just think that quietly. It's incredibly effective, but it has weaknesses too. Here is a weakness. What if you, first of all, imagine that you took 100-page proof to prove a statement, right? Because when we formulate the opposite of our statement, we hope it's false, but it's not obviously false, right? We're trying to get there. And suppose it took you 100 pages to get to that obviously false statement or two conflicting statements. Once you're done, you can throw out the middle. It's garbage. It's garbage. The things that you concluded are all false, and the things that you brought in, like the prime factorization, true or false, it's gibberish, right? So that's a weakness, that you cannot use the middle, only the very end, only the conclusion. After you have your result, the rest is useless. You don't have a nice little collection of true statements. You have a nice collection of statements that could be true or false, right? So that's one weakness. The other weakness is, what if we don't find a contradiction? What then? What if we don't find a contradiction? Exactly. I was hoping for the wrong answer. Well, then it's not true. Well, or we didn't look hard enough. If we don't find a contradiction, we learn nothing again. It could be that it's there, we just were too blind to see it, or maybe we didn't find it because it's not there. There were plenty of times when mathematicians stated, we call it a conjecture, that we think it's true, we suspect, but there is no proof. And then someone proves it, and a few decades later, someone proves that, that was incorrect. There is a boo-boo there. It might have been Euler or someone who knew Euler, who spent several hours on every Saturday for 8 years just to prove this other mathematician wrong, which he eventually did, because, you know, they hate each other sometimes, just like actresses would. You would think that mathematicians are wise creatures, therefore peaceful. Many of them are, but there is always exceptions. So so yeah, plenty of time we have found errors in proofs. In fact, you know what the field medal is? Nobel. So here is the anecdote. Nobel, his wife cheated on him with a mathematician. So when Nobel established the Nobel Peace Prize, he did not care for mathematicians. He skipped them. There is Nobel Prize in what? Physics, chemistry, peace, writing, doctors, I think, not mathematics. So mathematicians came up with, it's called the Fields Medal. But the Fields Medal, you have to be young to get it, which is kind of mean. You have to be under 40. And you know what was the most famous conjecture until just a few years ago? The most famous conjecture, we just got it proved, I think. I didn't read the proof. The most famous conjecture is called Fermat's last theorem. Let me state Fermat's last theorem. You know the Pythagorean theorem, right? The Pythagorean theorem say 3 squared plus 4 squared equals 5 squared. That's true. 9 plus 16 is 25. Fermat said, okay, go up to degree 3, degree 4, degree 5. The only numbers you will find that work are trivial, where one of them is 0, like 3 cubed plus 0 cubed is 3 cubed, right? So Fermat's last theorem, in a to the n plus b to the n equals c to the n, has no non-trivial solution for n equals 3, 4, and above. So a non-trivial solution is like 3, 4, 5. A trivial solution is make one of them 0, right? Then of course, so it is a trivial one, 2 to the 5th power plus 0 to the 5th power. Of course, it's equal to 2 to the 5th power, right? But you make them, oh, and this is all integers, I'm sorry. Has non-trivial A, B, C integers. Yeah, with real numbers, anything goes, I guess. So if we're dealing with integers, no a cubed plus b cubed equals c cubed unless somebody is 0. No a to the fourth plus b to the fourth equals c to the fourth unless somebody is 0. And the interesting thing about this was that Fermat didn't announce or publish this statement. I think they found it after his death. They were looking through his stuff. And I think it was his diary that he said, you know what, I just figured out this thing and the proof is so easy. I just scribbled it on the margin of the book, of a book. So the proof was so easy, I just scribbled it on the margin of a book. Well, imagine, they looked at every page of every book he's ever owned. And this thing was Fermat, what? I think he was working in the 1800s, so it has been a little time and no one could prove it. Fermat's last theorem was this conjecture that I think just a few years ago someone proved it. And then they gave him the Field Medal. And then it turned out that his proof was flawed. And by the time he fixed it, he was over 40. I don't think they took the Fields Medal back, but, well, I just wanted to tell you this story. That it happens plenty of times that we find error in someone else's work. It happens. All right. So let me tell you a story about proof by contradiction. So you can throw out the middle and we learn nothing if we don't run into a contradiction. These are the weaknesses. So let me tell you another story. In every age, there is the one, it's like the FBI's top wanted list. We have a list of conjectures that we find most important and most difficult, probably. You should look at, this was a much more modern mathematician, 19th or 20th century. His name is Hilbert. You can look up Hilbert's list. He stated 23 conjectures, and I think people are really taking him seriously and they're trying to knock off. And it might be possible that when he wrote this, Fermat's last theorem was on this list. He had, I think, 23 conjectures. He found most important. You can look up what is the most famous famous conjecture. I think it's called the Riemann conjecture. It has to do with complex numbers and half and whatever. I could state it, but I will state it in algebra 2, if you remind me. By then, you will understand every part of it. So Fermat's last theorem was, at his time, the most famous conjecture. Now, this one is the statement that I'm gonna, there is another statement I'm gonna state, which was very much like Fermat's last theorem, one of the most famous. Everyone wanted to hit that. Everyone who wanted to be famous was trying to do that, okay? So there was a famous conjecture. It was called the parallel postulate. It was called the parallel postulate. I should probably tell you about the difference between theorems and axioms. I might have told you at the beginning. What is the difference between these are the type of true statements we accept in mathematics. So here is the thing. We like to prove theorems, which means we start with a true statement and we arrive to our statement using logically correct steps. That's what it means to prove a statement. So a theorem, we prove them. And that means two things. Start with a true statement. And arrive to yours using logically correct steps. So here is the problem with this. This is very rigorous. We really like it this way. And by the way, whatever you see in books, lemma, proposition, corollary, these are all just different types of theorems. Lemma is usually, this is a difficult theorem, and its immediate conclusion is the really important thing. So it's a helper theorem before the big one. A corollary is something that falls out from a big one. Property, that's a theorem too. It's just, it will describe something. But it's theorems. All of those are theorems. We like them to prove. We like to see them proven. But here is the problem. Imagine that nothing is true. How on earth are you going to prove your first theorem? How are you going to go prove the first theorem if nothing is true? You cannot start, right? Now, early on, there was a very smart person. His name was Euclid, who realized this. And he said, we have to accept certain statements to be true. Just think of them as our starting true statements, and then we derive everything from there. He called them postulates, which sounds like some sort of a disease, but it's the same thing as an axiom. So a postulate was just an old-fashioned way of saying an axiom. So axioms, we accept them to be true without proof. You know, the distributive law is an axiom. To be true. Now, we don't like this a lot, so we want to keep the number down, and they should deeply, deeply agree with our intuition. So keep the number down. And Euclid actually axiomatized whole mathematics. The most famous work was geometry, but he just did the whole thing. And the work of generations of mathematicians before and after he was lost because he was perfect. No one needed to look elsewhere. He was a very, very smart man. So he axiomatized mathematics, this thing of having axioms, and from the axioms, we proved the first theorem. From the first theorem and the axioms, we proved the second theorem. From the first and the second theorem and the axioms, we derived the third theorem. This was done. Somewhere it's written down. We have this order of things. This sort of technique was immediately embraced by the mathematical community, and we do it that way ever since. I don't even know of anyone who tried something different. This is just so fundamentally, I don't know. I could not imagine any other system. So that's about. Oh, here is an axiom from geometry. After this class, look up Euclid's postulates. How many he had, and then what theorems he derived from it. Don't worry about the proofs. Some of them are tedious, but you can look up his postulates. Especially because I keep forgetting the number of them. So here is one from geometry. 2 points uniquely determine a line. That feels right. Here is an axiom from, I guess, algebra. For every positive integer, there is a next one. That's called the axiom of infinity. That's how we handle infinity, which is kind of funny because we just say, well, pick any of them, there is the next one. So we use finite terms somehow to talk about infinity. We try to be very, very clear. If someone is making you feel that math is somehow mysterious and foggy and makes you feel small, they're doing it wrong. Math should be demystifying things. This might be a little bit different because I'm This is a story I'm telling you. I'm going to get around to it. So I'm going to try to state the most wanted conjecture at the time. We're talking about the early 1800s. So Euclid axiomatized geometry, and he had, I don't know how many Euclid's postulates. He had a list of them. Let's just say 5. I'm not, just as an example. So he had axiom 1 or postulate 1, postulate 2, and axiom 5 had a name, the last one. It's called the parallel postulate. And it said the following: grab a plane and have a line on it. And outside of the line, have a point. There is no more than just one line that goes through this point and never intersects that line. It's the parallel, right? So that's the parallel postulate. That was his last axiom. Given a point and a line in the plane, there is just one. Passing through, there is just one line passing through the point, never intersecting the line. Unique, parallel lines are unique, I guess. Passing through the point and I'm not sure I need to write this. All right. That was the parallel postulate. And people thought, there was a conjecture in the air. People thought maybe the 5th postulate is really not an axiom. Maybe it's a theorem. And proving that was that that was the most wanted conjecture. You wanted to become famous. This is the thing that you had to do. So most famous conjecture, maybe the parallel postulate is really a theorem. Now, how would we go about proving it? Well, if it's a theorem, then you kick it out from the axiom list. The axioms we're down to 4, and if you can derive it from the theorems we have and the 4 axioms, then you're right. It is a theorem, right? So if you shorten the axiom list, you prove it from the shortened list and the theorems we have, well, I have to be careful because you cannot use all the theorems we have because some of the theorems use this postulate, right? So you kind of have to restart. So say you throw away this axiom and then you prove theorem 1, theorem 2, and you derive the same geometry and that particular statement, then it's a theorem. Does it make sense? So how to prove it? Okay, remove it from the axiom list. And use the shorter list to arrive to that statement. Prove it. And prove it from the shortened list. All right. So at the time of the story, there was this boy who was 17 years old, pretty young, very talented. His father was very smart too, but I think the kid was a little smarter. And at that time, the most famous mathematician, he was like a king. Everyone went to him. His name was Gauss. Friedrich Gauss was very, very well known, very famous. He was sort of the the king of mathematics at that time. And so everyone who wanted to publish something, people wrote to him. And so here is this young 17 years old boy, and he's exchanging letters with his father, and he says, you know what, I think I'm going to prove the parallel postulate. And the father says, no, start with something easier. You know, that's the hardest one. No one can get it. Why don't you start with something easier? Well, tell a 17-year-old boy not to do something. Guess what? He started to prove the parallel postulate. And he proceeded by contradiction. So what did that mean? He assumed axiom 1, axiom 2, axiom 3, axiom 4, removed this, and then he assumed the opposite of that. He assumed that if you have a line and a point, then you can draw several lines through the point that never intersect the line. And he started to conclude and started to conclude and started to conclude. And he concluded, and the contradiction just wouldn't come. But after a while, he realized, I'm never going to get a contradiction, but he discovered non-Euclidean geometry. Imagine that you're doing geometry on a sphere. Then lines become circles, right? And it's perfectly easy to draw a line, well, on a sphere, that would be a circle. And an outside point, there are plenty of circles that you can draw, right? You can tilt, just don't tilt it too much. Oh, I'm sorry. So on a sphere, lines become circles. And if you have a circle line and a point outside it, there's more than one circles you can draw through that point that doesn't intersect the line. Oh, and he had crazy things like, he got things like all the angles in a triangle add up to more than 180. And that's true too. Imagine in the sphere, you start at the North Pole and you come down to the equator, and then you come down the equator, but there is a right angle here, and then you meet like that. There is a triangle with 3 right angles. So crazy, wacky stuff. Instead of a contradiction, he discovered sort of the contours of a different geometry, no conflict. And he also discovered basically something that we call model theory, because it looks like not only that the parallel postulate is an axiom, but it's independent from the other in the sense that you can assume the 4 axioms and the parallel postulate. You can assume the 4 axioms and the opposite of the parallel postulates, and you get 2 different worlds. So this last one is sort of independent from the others. That's a very interesting part of logic, I guess. Model theory, not sure now. That is looking at things like axioms, theorems, and such. So that was a really big realization, and he sent all his results to his father, who sent it all to Gauss, and Gauss stole it, which was so sad because Gauss was so amazingly smart. I mean, he was just so smart. I don't know why he did that, but you know, he was working on this stuff obviously because this was the most, everyone wanted to prove that the parallel postulate is a theorem. So he was working on it, but he didn't come near as far as this kid. And what's interesting, well, what's sad is that after that, the kid never touched math again. So he was lost to the world of mathematics. But what's also really strange is that at the same time, same decade, there was a Russian dude who discovered the same thing, at completely independent of each other. So 3 people were stumbling into this, but I believe this boy was the farthest. He realized that you can set up a number. If that number is 1, we have our geometry. If it's bigger than 1, we're on a sphere. If it's less than 1, we're sort of like on inside of a sphere, something like that. And you have a systematic geometry, coherent in its own right, but with different rules. So that was one cool thing that I wanted to tell you about proof by contradiction. there was a semester when I did this proof. The square root of 2 is irrational. I did that proof as someone asked, is proof by contradiction important? And then I thought I should mention this story, and then he can make up his mind about it, whether it's important or not. All right. Any questions? All right, we have. So don't think that we are, I don't think we're done with the material, but the most important things we have done. And then there are things that we can leave it or take it. Let me start with the most interesting one. I want to show you how to do, it's a certain category of word problems, digit problems. And they're quite easy once you get that fundamental thing, which I'm going to explain. Let me just give you an example. So the digits in a two-digit number add up to 10. If we interchange the digits in the number, we obtain a new number that's 54 greater than the original number. Find the original number. So the problem is, okay, we can say, okay, let X and Y denote the two digits. But then if you write down XY, well, that's not a two-digit number. That's take the value of X, take the value of Y and multiply, right? So how do we sort of set up unknowns for digits and then express the original number? Right? You can have all kinds of math questions like the 3 digits multiplied to 20. Their sum is this and that, and then something about the actual number. So how do we take apart and then put back a number together? And the answer is pretty easy. Let me give you an example. For example, 437 is 4 times 100 plus 3 times a 10 plus 7 times a 1. But you see, here it is, the digits alone. So if you want to have a 3-digit number ABC, now right now it looks like 3 unknowns and you're multiplying them. If you put a bar over them, and you already saw repeating decimals doing this, now this is different. This is now the 3-digit number ABC. And if you want to talk about the 3-digit number and you want to do stuff to it, the way we do it is, well, A means 100, B means a 10, C means a unit, right? So it's 100A plus 10B plus C. That's it. Once you saw this, it's not that difficult. So we have a 2-digit number, and the first statement was that the digits add up to 10, right? So we can say, all right, let's go with XY. And then the first, if we have 2 unknowns, we should have 2 equations. Well, it says that digits add up to 10. That's easy. And the second one is, if we, what was it? I know 54, but less or more. The windows disappear so easily. I did not close that. It disappeared. All right, so, well, I can pull up another example, but then, oh, it. All right, so we're gonna do new numbers. Sorry. So it's add up to 10. We obtain a new number that's 36 less. Okay. So the digits add up to 10. And when we interchange the number, we shrink it by 36. So the original number, let's say this is the number, is 10x plus y. And when we swap the 2 digits, we get 10y plus x. And when the original number is bigger, 36 bigger, right? So this is smaller. If you want to make them equal, you have to add the difference to the smaller one. And now we have a very easy linear equation with two unknowns. I'm going to clean up the second equation first. So we have 10x plus y equals 10y plus x plus 36. Right? So we can subtract x, then we get 9x plus y equals 10y plus 36. We can subtract y, and then we get 9x equals 9y plus 36. Right? We can divide by 9. X equals y plus 4. So that simplified pretty nicely, right? So the first equation is x plus y equals 10, and the second one is x is y plus 4. Yeah, the first digit should be bigger, so when we swap, it shrinks. We can just use substitution, so we can put this into the first equation. Instead of x plus y, it could be y plus 4 instead of x, plus y equals to 10. So that's 2y plus 4 equals to 10. So it looks like y is 3. 37 and 73. So then x is 7. So the original number is 73. And then when we swap, we should shrink it. So yeah, 37 is less than 73, but how much less? Yep. So it works. Let's do another one. Any questions about this? Yeah, these are kind of lame. I have to write better ones. Okay, so here is the other version, kind of the same ballpark. So the tens digit in a two-digit number is 1 less than the ones digit. If we interchange the digits in the number, we obtain a new number that when we add the two, we get 99. Same question, find the number. And the window is here. So the tens digit is 1 less than the ones digit. I'm going to use AB now. So AB, and the tens digit is 1 less than the units digit. So that means that what is A is B plus 1 or B is A plus 1? Which one? A is B plus 1 or B is A plus 1? A equals B plus 1 or B equals A plus 1? Which one is good? Which one expresses this? Oh, maybe I'm saying the wrong thing. Which one? Enter into the chat box which one, or just that you're here, because I'm not sure. Hope at least the two of you are here. Okay. Yeah. It's just us now. All right, it's just the two of us. So, well, but that's something you should work on it. So the tens digit is 1 less. So this is 1 less. So A is 1 less than B. A is 1 less than B. Okay. And then when we add the two numbers, the result is 99. So the two numbers, well, this, if I want to go back, is 10A plus B. And if we add what we get when we swap the two, that's 10b plus a, and that's 99. So this is perfect for substitution. Let's just clean up this. I think this says 11a plus 11b equals 99, which means a plus b is 9. And then we can, into this line, we write a equals b minus 1. So instead of a plus b equals 9, instead of a, we're going to say b minus 1. So a plus b equals 9 becomes b minus 1 plus b equals 9. So 2b is 10, b is 5. And then a has to be 4. And indeed, 54 and 45, that's 99. Okay. So 45. Okay. Any questions? Well, another thing that I can show you is, you know, there is a lovely topic that we just couldn't get to it because first you have to learn how to factor, and that's kind of at the end of the course, but it's kind of too bad. There is a lot of, at the beginning we did divisibility, but we stopped with the prime factorization and GCF, but we shouldn't have had to stop. Let's just get a little glimpse into issues of divisibility. But we had to wait until you can factor out stuff. So here's the definition. Remember why 3 is a divisor of 21? Because of 7. So given integers n and m, no. Yeah, m is a factor or divisor of n if that exists an integer k such that m times k is m. So basically, yeah, I remember we used 3 and 21. So given 21 and 3, we can say that 3 is a factor of 21 because of 7. 7 times 3 equals to 21. And what's lovely that I could have said, there are 4 ways to say it. M is a factor of n, m is a divisor of n, or n is a multiple of m, or n is divisible by m. And this part of mathematics called number theory is looking at issues of divisibility, but the only thing we never do is divide. We express everything in terms of multiplication. So, for example, if you say divisible by 5, here is a really quick way to write it: 5k, where k is an integer. It means 5 times an integer. We sort of have k is kind of reserved to integer, but we're never going to want to find it or anything. It just exists. We don't really care. Some people use Greek letters for this. But this is how we say it's 5 times an integer. That's what it means to be divisible by 5. And so here are the things we couldn't do until now, is that, for example, if a and b are integers divisible by 5, so are their sum, difference, and product. Hey, the product is divisible by 25, actually. Well, if a and b, so here's the proof. If a and b are integers divisible by 5, then a is 5 times k, and b is 5 times L. For some integers, we are really not interested in. For some integers, L and K. Well, how about the sum? A plus B is 5K plus 5L. And we have to wait until factoring, because then we can say, oh, it's 5 times K plus L. And if K is an integer and L is an integer, so is the sum. So 5 times an integer, divisible. It's intuitively obvious, but this is a wonderful language that we couldn't get near it before factoring. A minus B goes the same way. Hell, A times B is going to be divisible by 25, right? A times B is 5K times 5L, and that's 25KL, divisible by 25, in fact, not just 5. So far, so good? So here is kind of a cute statement. If we square an odd number, the result has a remainder of 1 when divided by 8. That's 8. 8 is a pretty big number. To every odd number will this has a remainder of 1 when divided by 8. Let's try a few. So that means it comes right after a number divisible by 8 when divided by 8. Well, let's see, 5. 5 squared is 25. That's right after 24, which is divisible by 8. Okay, how about 7 squared? 49 is right after 48. 3, well, 3 squared is right after 8. Okay, 11 squared, 121. That's right after 120, divisible by just about anything, right? It has a lot of divisors. So this is a strange thing, because there are so many options. When you divide by 8, you can have a remainder of 0, 1, 2, 3, 4, 5, 6, and 7. And nobody will do 7 when you square. An even number will do probably an even remainder, and an odd number will just do 1. Isn't that strange a little bit? And the proof is really cute. So how do we say even number? How do we express a number is even? Well, even means divisible by 2, so it's 2k. For some k, we don't care. This is just shorthand for some k integer. Right? That's how we say it's an even number. And by the way, what happens when you square it? It's going to get divisible by 4, right? It's going to be divisible by 4 after squaring. And so how do we say odd number? We go 2k plus 1. And that's an interesting expression here, because we can think of k as a fixed thing, and then we get a fixed number for k. But if, let's do it this way, 2k plus 1. If we let k run through all the possible values, all the possible integer values, we pick up all the odd numbers. If k is 0, 2k plus 1 is 2 times 0 is 0 plus 1 is 1. If k is 1, 2 times 1 plus 1, that's 3. If now you see we talked about the slope. If we increase x by 1, y will increase by 2, and same with decrease. So it will pick up every odd number once as k runs through all the integers. So this is also how we denote all of the odd numbers in the whole wide world. It's just k cannot be fixed. It has to run around, take all values, 5 and so on. And negative ones too. If k is negative 1, we're talking about -1, right? Twice -1 is -2. Add 1, we're back to -2 times 2 is -4. Add 1, -3. So you see, we pick up every odd number. Okay, so the statement says if we square an odd number, the result has a remainder of 1 when divided by 8. Well, let's do it. 2k plus 1 squared. Work it. I'll wait. Just void it out. 2k plus 1 times 2k plus 1. K plus 1 times 2k plus 1. Exactly. No. What is 2k times 2k? So the first piece, I object to the first term there. That's right. So we get 4k squared plus 4k plus 1. Now, that plus 1 serves our purposes because we're saying the remainder is 1. So this number, it's very clearly divisible by 4, right? We can factor out that 4 and say 4 times k squared plus k plus 1. So here we are. This is already an interesting, cute result that if you square an odd number, it's never going to give you a remainder of 3 with respect to 4. It's going to, you square an odd number, it's going to be right after a number divisible by 4. Well, actually, we know it's going to be even a stronger result. It's right after a number divisible by 8. But the question is, where is that other 2 coming from? We have proved that the remainder is 1 when divided by 4, but why 8? We need to prove that this thing isn't divisible by 8, not just 4. And I find this beautiful. You see, if k is an integer, then k and k plus 1 are consecutive. 2 consecutive integers, one of them is even. So the fact that these are not just any 2 integers, but one right after the other guarantees that this product is even, right? So since k and we don't know which one, k plus 1 are consecutive, one of them is even. And you know that an even number times anything is going to be even. We didn't prove it, but one of them is even, therefore their product is even. So that's where the extra 2 coming from. So this number here is divisible by 8. And so the square of any odd number is going to be right after a number divisible by 8. Which is kind of strange because there are so many options divisibility-wise. So it's that bloody factoring that I was waiting for. This is just a lovely, lovely branch of mathematics. It's very beautiful. And it uses a lot of algebra. Let me see if I can think of other lovely but easy statements. Yeah, there is a lot about divisibility by 9. All the divisibility rules, we can prove it. You remember, so let's prove the divisibility rule by 9. So claim, actually, something much stronger is true. What we discussed is that if you add the digits of a number and the sum of the digits is divisible by 9, so is the number. Actually, more is true. If you add the digits and the sum of the digits will give you a remainder of 5 when you divide by 9, so is the number. You basically can replace divisibility by 9. Why? You can replace the sum of the digits. It has identical behavior. It has the same remainder. But let's just prove the divisibility rule. So a number is divisible by 9 if and only if the sum of its digits is divisible by 9. Okay. All right. So let's look at a 3-digit number. So let's look at ABC. Hey, we just did this today. So ABC is, we go back to the regular meaning, that's 100A plus 10B plus C, right? This is, if we look at the 3-digit A, B, and C, and we have to sort of take it apart digit-wise because we're trying to add the digits, right? So if you have 3 digits that form this number, this is how we get back to the number. And now what we're going to do, we're going to make 2 groups. And one group is going to be the ones that are for sure divisible by 9. And the rest is going to be the deal breakers or deal makers. So for example, 100 is 99 plus 1. So we can rewrite 100A as 99A plus A. And then this is the part that we don't have to worry about it. It's divisible by 9, no matter what A is, right? And then we take apart 10B as, well, 10 is 9 plus 1. And so 10B is 9B plus B. And there it is. There are 2 groups here. This is the group that has no saying. This part is for sure divisible by 9. So who determines whether this is divisible by 9 or not? If this sum is divisible by 9, so is the whole thing. But I should, just to be sure, I should factor out 9 times 11A plus B plus A plus B plus C. And that kind of tells you the remainder is the same. This whole number, this is the number, we just rearranged it. If the sum of the digits has a remainder of 7, when we divide by 9, the whole thing does the same, because this part is divisible by 9. Kind of cute. And then let's do 4-digit. So if you have something like ABCD, that number means 1000A plus 100B plus 10C plus D. And now take apart we split them into 2 groups. The group that's for sure divisible by 9, and the catch is that it's always 1 before a 10 power, right? If you take a 10 power like 1000 and you subtract 1, there is your 999. And that's why the rule is what it is, because 1000 is 999 plus 1. And this part, it doesn't matter what A is, this part is divisible by 9. Only this part will matter, and that's just one of them. Plus 99B plus B plus 9C plus C plus D. And so we have 9 times 111A plus 11B plus C plus A plus B plus C plus D. So again, if this sum here is divisible by 9, so is the whole thing, which is the number. If not, it isn't. And the remainder is getting preserved as well. So A, B, C, D is divisible. And by the way, same with divisible by 3, because anything that's divisible by 9 automatically is divisible by 3. 9K equals 3 times 3K. Here's the proof, right? If K is an integer, 3K is an integer, 3 times an integer, divisible by 3. But that's kind of obvious at this point. ABCD is divisible by 9 if and only if A plus B plus C plus D is divisible by 9. Kind of a cool thing. I'm wondering about the divisibility rule for, the easy ones, like the divisibility rule by 5. Remember that one? It's the last digit. It's because, let's take this ABCD. So divisibility by 5. Like, why is it enough to look at the last digit? Because the rest is automatically divisible. Divisibility by 5. So here is ABCD, which is 1000A plus 100B plus 10C plus D. And this part here is already divisible by 5 because it's divisible by 10, right? So we just need to look at the last digit. But again, if you want to rigorously prove it, we had to wait for factoring. There. What I'm thinking about is the divisibility rule by 11 is interesting. And I wonder, it might be a little above. Do you remember what it was? I didn't even state it in this class. The divisibility rule by 11 is interesting. Okay, here is a gigantic number. And there is a test for divisibility by 11, and it goes like this. Basically, we're going to make the digits into 2 groups by, we select every second. So some are underlined by green, others are enclosed with a red. These are the 2 groups. Add the 2 groups. And then subtract the smaller one from the bigger one. Now, if that difference is divisible by 11, so is the whole number. So here, 3 plus 6 plus 5 plus 0 plus, 3, 6, 5, 0 plus 3. What is that? 17. And then 8 plus 0 plus 1 plus 0 plus 4 is 13. 17 minus 13 is 4. This is not divisible by 11, neither is the number. So can we put a last digit here to make it divisible by 11? So if we put a number here, that will increase the green ones. This is the green ones, right? 0, we can go for a 0 instead of 4. So if I put here a 4, then this, oh no, that's not a 4. A 7, right? So if we are asked to put a digit here, then we can only increase the green group. That's already bigger, right? So we can increase this already bigger. So we can just grow the difference. And the next one would be 11 if the difference is exactly 11. So that means we want to add 7 to the difference. That means I think a 7 will do the trick. Because now the green is 3 plus 6 plus 5 plus 0 plus 3 plus 7 is 17 plus 7. What is that? 24. And 24 minus 13 is 11. That's divisible by 11. So is the number. Three, 8, 6, 0, 5, 1, 0, 0, 3, 4, 7 divided by 11. Doesn't look like it. Or that dot. It's too big for us to see. Let me cook a smaller one. How about 3, 8, 5, 2, and now let's fill it out so the number is divisible by 11. What 2 digits should I put in there so the number becomes divisible by 11? And we can check that one. This one was too big. 3, 5, 2. So 3 plus 5 plus 2 is 10. And 8. So if we make the second group 10, it will work. So we can do a 1, 1, or a 0, 2, or a 2, 0. Now it's a combinatorial question, like, oh, how many such number are there? Let's try the first one where I put 1, 1, 3, 8, 5, 0, 1, 2, 1 divided by 11. Worked. 3, 8, 5, 0, 2, 2 divided by 11 works. One more. 3, 8, 5, 3, 8, 5, 2, 0. 2, 2, 0 divided by works. Kind of cute. And there is an interesting reason for this. You have to split up groups. It's because the 10 powers behave, even 10 powers and odd 10 powers behave differently. They're not like 9. 9 is always under a 10 power. 11 is half the time above, half the time below. So when divided by 11, what is the remainder? Well, 10 to the 1 is 10. The remainder is 10. That's just 1 before, right? 10 is 1 before 11. But 10 squared, 10 equals 11 minus 1. And then 10 squared is 100. It's 99 plus 1. And then 1,000, if we played our cards right, if we add 1 to it, so it should be something divisible by 11 minus 1. So I'm sorry, 11, yeah. So we add 1. So that means that 1,001 is divisible by 11. So it's 99 times 11 minus 1. 99 times 11. 91. Right. 1,001 divided by 11. 91. So 91 times 11. Now it's 1 bigger. So so when the exponent is 1 or 3 or 5, let's see, then we are just 1 before a number divisible. Just think of 10. That's right, 1 before 11. So 10 to the 5th power, if we add 1, that should be divisible by 11. And it is. And then the even ones are the other way around. 99 is clear. 10 to the 4th, now we don't have to add 1, we have to subtract 1, so it's divisible by 99. Well, that looks obvious. How about 10 to the 6? 10 to the 6 minus 1 divided by 11. There. So this is kind of neat that every second 10 power behaves differently. So that's why we have to group them into 2 groups. All right, I'll stop here. Thank you. Thank you very much. I'll see you next week.